Hi, I got my hands on a bunch of these thermoelectric Peltier devices thanks to circuit specialists. I've never used them before, but from what I know, when you apply electricity to them, they pump heat. Well, let's power it with 12 volt DC. I know the theory behind it, but I haven't really experienced one. What? It burn freezes. It's like you're naked in space and your side facing the sun is boiling hot and the other side is freezing cold. I knew this would happen, but when you really experience it, new questions pop in your head. Like all my life, when I ran electricity through a conductor, it always heated up. Except now it's cooling down and it's heating up on the other side. It kind of works like my wife. While the rest of her body is at boiling temperature, her feet are at absolute zero. Okay, let's power it up again and look at it with my thermal camera. Right now, both sides are at the same temperature. And if I power it up, this side cools down quickly while the other side heats up. Oh, it's burning. I shouldn't run it at maximum power with no heatsink. Running it at 5 volts. And one side heats up while the other side cools down. So it's like 29 degrees here and 60 degrees here. So there's like 30 degrees difference between both sides. And if I flip the voltage here, you see the cold and hot sides flip too. Now this side is cooling down and that side is heating up. If I let it run for a while, the cold side heats up too, but it seems like the device is keeping the temperature difference constant, around 30 degrees at 5 volts. And the temperature difference between the two surfaces is power dependent, so at maximum power, the difference can be 60 to 70 degrees. These things work based on Peltier effect, Seebeck effect, and Thomson effect, which is basically the extension of Seebeck and Peltier effects. And all these are different manifestations of the one thing that is the thermoelectric effect, which happens when two conductors with different materials touch each other. The Seebeck effect is when there is a temperature difference between the junction of two materials and rest of it, a voltage is created across the junction and acts like a generator. The voltage is typically very small, in order of microvolts, and increases with more temperature difference. Measuring that tiny voltage, you can measure the temperature. That's what they do in thermocouples, joining two different wires, chrome and aluminum in this case, and you can read the temperature on the meter. In the Peltier effect, if you run current through the same joint, it can cool down and absorb heat, or it can heat up and radiate heat depending on the direction of the current. The problem is that I have no idea what happens in atomic quantum level that passing electricity through two materials can cool it down. I read somewhere that the electrons move the heat away. What the hell does that mean? If you know a good explanation, please leave it in the comments so I learn it too. Or if you want to learn math and science, then check the sponsor of this video, brilliant.org. Such professional, much interactive, tons of math and science courses with interactive problem solving and quizzes to make sure you learn what you want better. So sign up for free at brilliant.org/ElectroBOOM to get access to a lot of free courses already. But using my link, you get 20% off of the annual premium subscription that gives you full website access for less than $10 a month. So, this device is fascinating. For whatever reason, when you run current through it, it pushes heat from one side to the other, creating a temperature difference. Like if both surfaces start at 30 degrees Celsius, running current can make one side 0 and the other 60 degrees. But it also wastes tons of power, 50 watts max for this guy, so it heats up quickly while the temperature difference remains around the same. So one side could be 100 degrees and the other side 40. But if I can somehow cool down the hot side to say 50 degrees Celsius, then the cold side could be minus 10 degrees. The cold side would suck the heat from the environment and pump it to the hot side. That's why I bought a bunch of heat sinks to experiment with. So I attached the device and heatsink using a thermal compound that fills the gap between the two and provides a very good thermal conductivity. The metal heatsink with so many fins creates a large surface area to transfer heat to air better and cool down. Okay, let's give it a try. Oh, look at that! The surface is getting colder. Great. But as the heatsink is getting warmer, the cold surface is going up too. Which means we have to blow air with a fan on the heatsink to keep it cold. Or even better, just place the heatsink in cold water. And we power it up. And there it goes. Of course, as the water slowly heats up, the temperature rises too. Running cold water would help, but that wastes a lot of water. Minus 11 degrees. Let's add some water to the surface and power it up and see what happens. And zip! It all freezes. And if I disconnect the power, bam, it heats right back up. These Peltier devices, or shall we call them thermoelectric devices, work on the same principles I talked about. But instead of one junction of two different material, there are many junctions placed in series like this between two surfaces, made of P and N semiconductors. Running current through them creates a temperature difference. Also, if you place a temperature difference between the two surfaces, you create a much higher voltage because of so many junctions in series. Flipping the temperature also flips the voltage. Let's give it a try. I have a box of tea with metal bottom, and if I pour boiling water in it, it creates a voltage at the output of the device, around 2 volts. So I can use this to power something. Here I have a 10 ohm resistor, and if I connect it to the output, right now I'm drawing like 160 milliamps from it. Of course, the voltage drops as the hot water cools down and the heatsink heats up, and temperature difference gets smaller. In general, thermoelectric devices are pretty inefficient to create either cool or voltage. Their main application is in those small cooler or fridges because they are light and small. Now I want to put 9 of these modules together to create a cooling surface slash a generator if possible. And so I bought a big fan to blow on the heat sinks and a bunch of screws and a wood board. Let's put them together. The hell? My camera of 6 years just blew up. Well, now I'm stuck with one camera and it doesn't have a microphone input, so I can't really use my wireless lapel anymore. Audio quality down. Here, my window of opportunity is made. Now I have to just install these heat sinks in it. Come on. Okay, so let me show you what we've got. The fan here will blow up directly into the heatsink. I raise the heatsinks up a little bit so that the air has a chance to get over to all the fins of the heatsink. And I put those pieces of wood in the bigger channels to block them a little bit to make sure that the air gets to all the fins. And the heatsinks are all in parallel, so the air escapes from front and back vents. I noticed something interesting. It seems like because the fan is turning this way, maximum airflow is coming out this way and out that way. And there is very little airflow in these areas, so that might affect the temperature performance of the heat sinks. So I guess the air is not just coming straight up, it's twisting. And I guess that's where the knowledge of fluid dynamics would have helped. I've got an idea to make the airflow better using a CD cover. Let's hope it works. So here's what I've made for the fan, and I think I've seen it on some other fans before. Basically, my fan, when it blows, the air spins up like this. But now with these fins, the air, instead of twisting, it will hit these walls and comes straight up. But now I've made them curved. So what happens is that when the air hits here, it slips inside, so all these fins push the air inside where there is almost no airflow, and when the air hits on the outside curve of the fins, it is pushed out this way, so it spreads further out. So instead of one twisting column of air, hopefully it's more spread out and even. Okay, let's see if it helps. It doesn't really help that I placed the fan too close to the fins. You know, if there was a greater spacing between them, the air would be much more even and would cover more of the fins. Well, you know, I'm an electrical engineer. I'm not really qualified to do this kind of mechanical stuff. Hey, look at this. These two, the airflow feels almost the same. This one feels a little bit less, but it's much more even now. Okay, now that everything is in place, I'm gonna cover between them with silicone, not only to keep these devices in place, but also to further isolate the hot and cold surfaces. Or at least that's my thought. Okay, I need a small pan. I don't want to have to cut a piece of sheet metal. I want it nice and straight like this, but small. I want something square and small. Don't seem they have it. This looks good, but it's part of a napkin holder. Maybe I should just buy the whole thing and cut this out of it. Ooh, these metal doors are perfect. If I can find one without the handle. Fine, I'll just buy one of these and cut it. You know, some people play Minecraft in their channel. I'm kind of doing the same. I'm mining for money, then go to the villagers to trade for tools and equipment and make my own stuff. Hey, I'm a gaming channel. Now I'll attach this piece of metal over my Peltier devices using thermal paste, and hopefully this piece of metal will help spread the heat evenly to all the devices. And so it's done. Just took a week or two. And thanks to my Patreon support, I got a new and improved camera. So to thank them, I'll buy them 4 3D printers. Thanks for keeping my videos afloat. Now to use it as a generator, I put all the modules in series, hoping that the sum of voltages is usable. So here I'm boiling some water. And with my 24-volt fan running, I put my water on top of it and... that's it! I guess my heatsink in water was creating a larger difference. What is this good for? It's a joke. I guess I can turn on 2 white LEDs in series. Oh look, one of them is red. So a 24-volt fan, a pot of boiling water, and hours of work to turn 2 LEDs on? I think somewhere it said if the module is good for cooling, it's not good for power generation. So it better cool. Now to make it a cooler, unfortunately my power supply can do 10 amps maximum, while every module can take 5 amps max at 12 volts. So I put every 3 modules in series and put the branches in parallel so that I can at least do 3 amps per module. Not ideal, but hey. I'll run the unit and the fan at 24 volts, so 8 volts per module. Look at this, it's cooling quite well. Well, now that it's almost settled, it's running 8 amps at 24 volts, so around 190 watts. I'm sure if I contain this, it will get even cooler. Unfortunately, running more power through my modules won't make much of a difference because my fan can remove a limited amount of heat. So instead of this side getting colder, my heatsink will get warmer. Look at all the condensation. But it works great as a fridge. If I want to make this surface super cold, I can put my heatsink in water or ice. Maybe something to try in the future. In any case, I learned some good stuff doing this project. If you also want to learn math and science, then Brilliant.org is your friend. It's like a teacher you never had. You learn on your own time, learn what you enjoy for your job or to increase your skills, solving fun problems and taking quizzes. Very useful. For some reason, I really enjoy geometry and its problems. It's like a game to me. So to keep my skills sharp, I'm taking their Geometry Fundamentals course, doing a series of cool problems. It's a great mental workout. If you really like to advance in math and science too, learning what you like professionally at your own convenience, then go to brilliant.org/electroboom and sign up for free and get 20% off for the first 200 viewers. And thanks for watching.